In section 15.2, we learned how to compute a single integral over a curve rather than an interval on the x-axis. Today in 15.5, we're going to learn how to compute a double integral over a surface. So again, that same kind of concept, but just upping it one dimension. But before we do that, I'd like to recall something that we learned in the previous chapter, section 14.4. We learned how to find the surface area of a surface. Now, we were going to let that surface be denoted by the lowercase Greek letter sigma. And we were always assuming that our surface was written of the form z equals f of xy. And in that case, what we were doing is we computed the square root of the sums of the partial derivatives squared, where if you'll recall, I just noted that this one is coming from the fact that this is del z quantity squared, which is itself, whoops, which is itself one. And so we added up those partials, squared them, added them up, and square rooted. And then we took the double integral over the region R. And that region is just the projection of the surface that we are trying to compute the surface area of. So we identify what surface area we're trying to compute, and then that determines our region. So we're going to build upon this model here for surface area in order to compute double integrals over surfaces. So before we get there, let's talk about what a curved lamina is. A curved lamina is an idealized object that is thin enough to be viewed as a surface in 3 space. So what I like to think of is, for example, a really thin piece of sheet metal that may be curved. So something of that nature where we're going to neglect the thickness of that object and just think of it as an infinitesimally thin surface. We're going to model a lamina by a smooth surface sigma. So again, we're still going to use that notation for a surface. We wish to compute double integrals over such surfaces, and the following theorem is going to provide us the formulas that we'll need in order to compute these surface integrals. Now we have 3 different setups depending on which variable we're going to solve for, x, y, or z. So for this first theorem, or for the first part, I'm going to assume that we have z solved for explicitly as a function of x and y. So let's suppose our surface is solved for z. Let r be the projection onto the xy plane. Notice that that xy matches the variables that are in your z equation. So if sigma has continuous first partial derivatives on R and f of xyz is continuous on sigma, then again, notice that z is missing. So we're evaluating our function f at that g of xy function. And then we still have this integrating factor that's exactly the same as what we saw up here when we were computing surface area. So again, I'll emphasize, we take the partials in x and y, z is missing in all of this equation. So when we're computing these equations, I will refer to this term as the integrating factor. And oftentimes I like to solve for this integrating factor first, right out of the gates, before I even set up my double integral. All right, let's take a look at the other parts of this theorem. In part B, we're assuming y is solved for explicitly, and then we have a function g of xz. In this case, we want to omit y, so we have our g function there. And then again, now look at these partials. I'm taking the partial of y, but this time with respect to x and z, our plus 1 is now del y, quantity squared. And then for our final part of the theorem, I'm going to assume that x is solved for in terms of yz. I'm going to replace the x component in my function f with that g function, and then I'm taking the partials of x with respect to y and z. So just subtle differences here. It's the same setup, but make sure that you're identifying which situation you're in so that you set up your double integral appropriately. Now, if your surface isn't solved for one variable to begin with, you can choose which one of these you want to use. And sometimes a choice is better than another. So take a look at your function, see what's going to make your integration simpler, and just go from there. So we have three examples here working with these surface areas so that we see a lot of exposure to these types of problems. So number 6, evaluate the surface integral. We have a fairly simple integrand here. Sigma is the portion of the plane z equals 6 minus 2x minus 3y in the first octant. So I just want to take a moment here to remind you that the first octant just means that X, Y, and Z are all greater than or equal to 0. It's kind of the equivalent of the first quadrant, but we go up a dimension, and so we now have 8 octants rather than 4 quadrants. All right, so let's compute our integrating factor. First, I'm going to note here that our surface sigma is solved for Z as a function of X and Y. And so then from that, we're going to identify our integrating factor. All right, so I'm going to take the square root of the partial of z with respect to x, which is a -2 squared, the partial of z with respect to y, which is a -3 squared, and then the partial of z with respect to z is 1. And then let's go ahead and simplify. This is the square root of 4 plus 9 plus 1, which is the square root of 14. So this is a unique case where our integrating factor is a constant. Typically, we'll actually have variables in here, but since z is a plane, everything is linear, so all of our partials were constants. So let's set up our double integral. I'm going to leave it generic at first as over our region. We're going to keep our integrand the same, x plus y, but we're going to tack on our integrating factor and then set up our dA. So the question becomes, what is the region in the plane that we're integrating over? So let's check that first. We need to project our surface sigma onto the xy plane. So we're going to let z equal 0. So what that gives us is 6 minus 2x minus 3y equals 0. So I'm going to solve. 3y equals 6 minus 2x, or y equals 2 minus 2/3 x. All right, so what we see is we have a line that's being projected down. Now here again, I want to remind you, we only care about the first quadrant, which means when we project down, we only care about we only care about the first octant in 3 space, which means in the projection, I only care about the first quadrant. All right, so I have a y-intercept of 2. And then let's see, an x-intercept of 3. So I'll just draw the line segment, even though it goes on, since I only care about the first quadrant. And then here's our region R. So at this point, we're computing a double integral. You need to make the decision. Are we going to work in rectangular coordinates or polar coordinates? Here, this is not a polar region, so we're going to stick with rectangular coordinates. And I am going to take a vertical slice. So here my thickness is in the x direction. So when I set up my integration, I'm going to keep that inside the x plus y times the square root of 14. I'm going to set up a dy dx for my differentials. X is ranging as low as 0 and as high as 3. And then I'll just remind you this equation was 2 minus 2/3 x. So y is ranging from 0 up to that equation, 2 minus 2/3 x. All right, so we have our setup. Now it's just a matter of carrying out this double integral. If you want to just stick your constant out front, that is perfectly fine. And now I'm going to integrate with respect to y. So this is xy plus 1/2 y squared, where y is ranging from 0 to 2 minus 2/3 x. And so this is getting just a little bit hairy. We're going to have to FOIL out this term here when we add it in. And I'm just going to preemptively distribute this x here. All right, so if I distribute my x, I get 2x minus 2/3 x squared. Then I'm going to leave my 1/2 out front and I'm going to go ahead and FOIL that y that I'm plugging in. So that becomes a 4 minus an 8/3 x plus a 4/9 x squared. And so let me do one more step to simplify. Let me combine like terms before I integrate with respect to x. So it looks like my only constant here is a 2. For linear terms, again, remember I have to distribute this 1/2. So I have a negative 4/3 at the back, a positive 2, which is a positive 6/3. So 6/3 minus 4/3 is going to leave me with 2/3 x. And then for the squared terms here, again, I need to distribute my 1/2. So at the back, I have a 2/9. At the front, I have a negative 2/3, which is a negative 6/9. So negative 6/9 plus 2/9 leaves me with a negative 4/9. Okay, and now I'll just carry out this single variable integral, rewriting my square root of 14. I have 2x plus 1/3 x squared minus 4/27 x cubed. And this is all for x ranging from 0 to 3. 0 is going to drop everything out. So I get 6 plus 3. Notice here 3 cubed is 27, so those are going to cancel, minus 4. So I have 9 minus 4, which is 5. So a final answer of 5 square root of 14. All right, so let's just back out a minute here so that we can see it in full. Again, when you're looking at these problems, you need to identify, first of all, which part of the function you're using. Since this problem was already solved for z as a function of x and y, we used part A of the theorem. We computed our integrating factor. We generically set up our double integral, and then we projected onto the xy plane to see that region of integration, and then set up our limits of integration appropriately. Once you get to your setup, you're really just relying on your knowledge of double integrals from 14.1, 14.2, and 14.3 to carry out the physical integration. All right, let's take a look at our next example. Example 20, we want to set up but do not evaluate an iterated integral equal to the given surface area or surface integral by projecting sigma onto A, the xy plane, B, the yz plane, and C, the xz plane. So we just want some practice in how to set up these surface integrals, but not actually carrying out the integration. So I really like this problem because it gets you to use all 3 parts of that theorem on page 1 of the notes to become familiar. So first of all, let's go ahead and just sketch what our surface looks like. Okay, so we have that our surface is the portion of the sphere in the first octant. So here again, the first octant means that we only care about the positive x, positive y, and positive z. So it's going to be that portion of 3 space that's coming out of the plane of the page, given this coordinate axes that I just drew. And we have a sphere of radius A. So I'm just going to draw that octant of the sphere. And all of these are out A on each of the coordinate axes. So we have this eighth of a sphere. And let's take a look here. Part A, we want to project onto the XY plane. So what that means is we want to solve for Z as a function of X and Y. Now here, since we only care about the first octant, I'm only going to take the positive square root. So I'm going to emphasize that by writing a plus sign. This is going to be the positive square root of a squared minus x squared minus y squared. So here's our surface equation with z solved for. From this, I would like to compute my partials of z. So let's start with partial z partial x. All right, I know that the chain rule is going to kick out a negative 2x on top because that's the partial of the inside with respect to x. And then on bottom here, when I pull that 1/2 power down in front, I'm going to get a 2 on the bottom, and then I get a negative 1/2 power. So it's pushing this square root to the denominator. And we've seen these types of derivatives before. Now here, of course, I can cancel out my 2's on top and bottom. And then based on this partial, we can see here that the partial with respect to y is going to be exactly the same, with the only difference being a negative y on top. All right, so we have our two partials. Let's put these together to find our integrating factor. Remember, I want to take the square root of all of the partials squared and add it up. So the x partial squared is going to be x squared over a squared minus x squared minus y squared. The partial with respect to y squared is y squared over a squared minus x squared minus y squared. And then I want to add 1, but instead of writing it as 1, I'm going to write it as that common denominator. So a squared minus x squared minus y squared over that same expression. And this is all a giant square root. And now that we wrote this with common denominators, I can add straight across the top. Notice that my plus and minus x squared and my plus and minus y squared cancel. And so my integrating factor reduces to a squared over a squared minus x squared minus y squared. All right, kind of a hairy integrating factor here, but things are going to work out in our favor. Remember, what we're looking for is the surface integral over sigma of x z ds. There, that ds differential tells you that this is a surface integral. But we don't know how to integrate with a ds. We know how to integrate with a dA, right? We know how to integrate over flat regions in the plane. And so let's transform this to a double integral in the plane. And so to do that, we pay for it with our integrating factor. Now look, what I have is xz. Remember that I want to replace z with what I had solved for in terms of x and y, but I'm also going to multiply by my integrating factor. So this z is going to cancel with this denominator. And so I'm not even going to show that step, but what I get is an x times all that's left over of my integrating factor is a square root of a squared. A is positive because it's a radius, so that is just a dA. And so let's take it one step further and just set up the double integral, but then we'll stop. All right, we're projecting onto the xy plane. So in our picture here, if I project what I'm seeing is this quarter circle. All right. So you can either choose to leave this in rectangular coordinates or polar coordinates. It's up to you. I'm going to leave it in rectangular since we're not actually carrying out the integration. But probably if I was going to do the integration, I would set it up in polar coordinates. So when we project, remember this equation on the xy plane is x squared plus y squared equals a squared. I'm going to set up a dy dx integral. So x is ranging from 0 to a, and y is ranging from 0 to the square root of a squared minus x squared. And so this is where we're going to leave our answer here in part A. We have formally set up our double integral, but we are not going to evaluate it. Part B is going to be very similar. We want to instead project onto the YZ plane, which means I want to solve for x. Here again, I'm going to take the positive square root of x since I'm looking at the first octant. And my partials are going to be very similar. So I'm just going to go ahead and skip to my integrating factor because it's going to be so similar to what I had in part A. I'm going to get an a squared on top, but instead of the x squared and y squared, I'm now going to have a y squared and z squared. So I have a squared minus y squared minus z squared. So saving some time just looking at the similarities between these problems. I'll just write that out. And so now let's set up our surface integral. We're starting with the surface integral of xz dz. Here again, I would like to replace x with what it's equal to. That is going to cancel out with the bottom of my integrating factor. And so this becomes the double integral over the region of ZA dA. And whoops, I just noticed I made a mistake here. This DZ should have been a DS. So let me correct that here in blue to call your attention to it. That was just a typo. And so now we need to figure out how we're going to set up our limits of integration. If we go back up to this picture here in 3 space and we project onto the YZ plane, I'll shade it in blue here. Again, it just looks like that quarter circle. So we're going to have a very similar setup in part B. So this becomes the integral from 0 to a, the integral from 0 to the square root of a squared minus y squared of ZA dx, excuse me, dz dy. All right, and we will leave this right here. All right, so for part C, we now want to project onto the XZ plane. This one is going to be slightly different because remember our integrand had X and Z. It did not have Y. So we won't need to change that integrand by substituting in, which means we'll see our entire integrating factor here in this third double integral. So let's go ahead and take a look here. So in part C, I'm going to solve for y, again, taking the positive square root because of our restriction of the first octant. And again, our integrating factor is going to be very similar, so I won't go through and reinvent the wheel. I'll just write it out here. I'm going to have an a squared on top. On bottom, I have a squared minus x squared minus z squared since we have solved for y. And so now let's take a look at our surface integral, which was x z ds. Again, x and z are fine. We want our whole integral in terms of x and z. So I'm going to leave those. And then I pay for the surface integral with my integrating factor. If you wanted to rewrite that numerator as an a, that would be fine. But we can't get rid of the square root on the bottom. And then we need to just set up our limits of integration. So let's look back up at our original picture. I'll grab a different color here. We're now projecting onto the XZ plane. So we have this quarter circle. X is going to range from 0 to a. Z is going to range from 0 to the square root of a squared minus x squared. And so we can set up our limits of integration accordingly. 0 to a, 0 to the square root of a squared minus x squared. And then we have xz times a over the square root of a squared minus x squared minus c squared. And here we chose to integrate in the order of z and then x. All right, so hopefully this problem illustrated the different ways that the theorem can be applied and how it might affect your integral. In this particular example, I don't really see a benefit of using a over b, but certainly c leaves us with a much more complicated integral. So you really want to check on the interplay between the integrand and the integrating factor to see if you get any cancellation like we did in this problem. All right, to finish off the section, we have one last application and then an example to illustrate it. And the application here of surface integrals is finding masses. So we have a remark here: if sigma models a lamina, and if f of x, y, z is the density function of your lamina, all right, then the mass of the lamina is given by the surface integral of your density function over your surface of your lamina. All right, so in other words, we're just going to integrate the density function over that smooth surface that's representing your lamina. So again, if you think of a piece of sheet metal that's curved, this is a way that we could compute the mass of that sheet metal as long as we knew the density of the metal. All right, so 30 is just going to use this mass equation. It says find the mass of the lamina that is the portion of the cone z equals, I'm going to emphasize this is the positive square root here, square root of x squared plus y squared between z equals 1 and z equals 4 if the density function is x squared z. So if I just look at the traces in z equals 1 and z equals 4, I get 1 equals x squared plus y squared if I square both sides. And I get 16 equals x squared plus y squared. So this is z equals 1, z equals 4. So let's go ahead and just sketch this cone so that we can see what we're working with. So here's z equals 1, 2, 3, 4. And at z equals 1, I want a circle of radius 1. And at z equals 4, I want a circle of radius 4. I'm just going to eyeball it here. And then connect those traces. Okay, and since we have z solved for, we're going to want to project down onto the xy plane. So I'm going to do that in red. So we're seeing the circle of radius 1. and the circle of radius 4. And so we see that our region is going to be this annulus here, this ring. It's not the best sketch, but gets the point across here. And so next, what I'd like to do is I'd like to figure out what my integrating factor is going to be. So let's compute partial z partial x. It's going to kick out a 2x on top, and on bottom, I'm going to have a 2 square root of x squared plus y squared. And so again, our 2's cancel. And then y is going to be essentially the same. So del z del y is y over the square root of x squared plus y squared. All right, so let's compute our integrating factor. It's going to be the square root of x squared over x squared plus y squared plus y squared over x squared plus y squared. And for once, I'm just going to leave it as plus 1 because you'll note here that the sum of these first two is equal to 1, right? I'm going to get an x squared plus y squared over an x squared plus y squared. So hot dog, our integrating factor, just becomes the square root of 2. Heck yes. So now let's set up our mass equation. According to the remark up above, the mass is computed as the surface integral of the density function, in our case, x squared z ds. So now what I'd like to do is I'd like to transform the surface integral to a double integral over the region R that I have defined there. So first, let me just set up the integral, and then I'll worry about setting up the limits of integration. I don't want z in my integrand. So I'm going to replace that with the square root of x squared plus y squared. And then I'm going to add my integrating factor of the square root of 2 dA. Now, this problem is just absolutely begging us to use polar coordinates in two ways. One, our region of integration is circular in nature, so that's a tip off. And two, I see an x squared plus a y squared in my integrand, which really wants to be an r squared. So let's set that up here. I'm going to note that this term is going to go to a single r. My dA is going to go to an r dr d theta. My x squared is going to go to an r squared cosine squared theta. All right, so keeping all of that in mind, let's set up our limits of integration. For theta, since we have a full 360-degree annulus, I want to go from 0 to 2 pi. And my radius, remember I had previously figured that out, these can be written up here as r equals 1 and r equals 4. So my radius is going from 1 to 4. And then using my setup inside, I have, looks like 4 r's. So r to the 4th. And then I have my cosine squared theta. And I have my square root of 2 here out back, which can most certainly be pulled out front if you would like. All right, so let's integrate with respect to r first. I'll write my root 2 out front, recopy my first integral, and I have a 1/5 r to the 5th, where r is ranging from 1 to 4. And then I have my cosine squared theta d theta. All right, so what the heck is 4 to the 5th? 4 times 4 is 16 times 4 is 64. 64 times 16 is what we're looking for. 24, carry the 2, 38, 64. And so we get 1,024. That is apparently 4 to the 5th. So I have my square root of 2. Then I have 1,024 over 5. And then I have my integral from 0 to 2 pi. Oh, hey, and let's not forget I have to plug in 1. So let me back it up here. So I need to subtract a 1/5. There we go. And then I have the integral from 0 to 2 pi of cosine squared. Now, in order to integrate cosine squared, I'm going to use the half angle formula. I'm going to swap that out for a 1/2 1 plus cosine of 2 theta. All right, and now I can continue on here with my integration. So I have 1023 root 2 over 5. And then when I integrate, I get a 1/2 theta plus a 1/4 sine 2 theta, where theta is ranging from 0 to 2 pi. The sine function here dies at all integer multiples of pi. And of course, 0 is 0. So I'm just going to kick out an extra factor of pi. So my final answer here is 1023 root 2 over 5 pi. All right. And so this is the mass of the lamina, which is shaped like a truncated cone with that given density function. All right, that concludes our notes for this section.